Hello and welcome to day 15 of Advent of Code. We have two more puzzles to solve today. Again, we are using Kotlin. I'm curious how hard they will be. Yesterday, part 1 was kind of straightforward to solve, just following the steps in the example. Part 2 was quite hard. I needed quite some time to find a solution for that. And yeah, let's see how day 15 is. I switched my red Santa Claus hat with a green hat, like an elf's hat. And yeah, really interesting how this looks like on a green screen. The glasses are green as well, but that is not really visible yet. Maybe later on, once we have different backgrounds. Anyhow, let's start with day 15. You've almost reached the exit of the cave, but the walls are getting closer together. Your submarine can barely still fit. Though, the main problem is that the walls of the cave are covered in Chitons? Chitons? It's a Chiton. Alright. Never have seen those. And it would be best not to bump any of them. The cavern is large, but it has a very low ceiling, restricting your motion to 2 dimensions. The shape of the cavern resembles a square. A quick scan of the Chiton density produces a map of risk level throughout the cave. Your puzzle input, for example. Okay, this is a map of risk levels. Let's fix the window. You start in the top left position. Your destination is the bottom right position, and you cannot move diagonally. The number at each position is its risk level. To determine the total risk of an entire path, add up the risk levels of each position you enter. That is, don't count the risk level of your starting position unless you enter it. Leaving it adds no risk to your total. Your goal is to find a path with the lowest total risk. This example, a path with the lowest total risk is highlighted here. Okay. The total risk of this path is 40. The starting position is never entered, so its risk is not counted. What is the lowest risk of any path from the top left to the bottom right? Alright, so we need to implement a pathfinding algorithm, and we might have multiple options to do this. Well, let's switch to IntelliJ and create all the files for today, and then let's see. Day 15. So package, and then we need day 15 file. No, stop, not a txt file. This is obviously wrong. It should be named day 15, and somehow I moved it into a package day 15 in day 15. Oh my god. How can I move this file up? Okay. Yep, now get rid of this weird package. We will need a main function, we will need a part 1 function, and then later for part 2 a function, and I'm already afraid of what part 2 will be, because part 1 is already an interesting problem. Let's create a test file. Yeah, the approach of using the example and adding a test case for that was super helpful, made debugging much easier, and let us find problems earlier. So we need the input. Oh wow, this is much larger than the example. Get the input, it here. We name it day 15. All right. Where do we start? We want to read this in, and we need a representation of this thing. And currently I'm thinking of having again a list of lists so that we can use the coordinates. Navigating is essentially visiting neighbors. That's something we already implemented in this adventofcode. And the example makes it look like we only need to go down and right. But I feel like they are fooling us, because it would be much easier if this was the case, but I don't think it is. Because if we imagine going down here would be a 9, and going left and this way would be a 1, kind of. Then this would be much cheaper to go left. Like, let's say go down and then left and around a block of 9s somehow. Yeah, so we definitely need to go left as well, and maybe even up. Especially if you look at this huge thing here. That will definitely require maybe going down, then maybe left, up, and in a weird shape. And this also makes me want to print the path. Would be interesting if we find a solution how it looks like. We can also compare this to this solution here. And visually it's much easier for us humans at least to figure out, is this the right path? Okay, but how do we find a path? I can see multiple options. One is the simplest one, brute forcing. We go from every position to every position and then expand and make sure we do not visit one multiple times, because if we go in a loop, this is always longer than not going the loop. So that means that we go every possible path until we are at the end. For this kind of input, that might be a lot. So maybe we need to be smarter than that. If we, like, the one thing that comes to my mind immediately is the A-star algorithm, which is a search kind of pathfinding algorithm. Here's an example, which we kind of could use. Here you can see that it's navigating around the black squares, which is something we do not even need. We can just find a path much easier. We do not have any blockers in our way. Maybe that will come up in part 2 actually. That would be interesting. To say like everyone is a block we cannot pass, like that would be a problem. And that is definitely smarter. Or yeah, another option here, Dijkstra, which might be simpler to implement, where we essentially need to remember which path. Do I remember this correctly? We need to remember which path It's kind of like brute force, but we remember how expensive it is, and then only follow the cheap or the currently cheapest path until we are at the end. That's maybe something we could do. We start here, we look at all neighbors, and for all neighbors that we haven't, for all neighbors we calculate how cheap is it, have we visited them already, or if not, and then for every point that we have visited we remember what is the cheapest path to it. Like if we are, let's say this one way we could end up here is 1131 or 1121, which this way is cheaper, so we would remember to this one the cheapest way was from here and from here to here, and then at the end, if we are here, if we always look at the cheapest way, then we might have found the cheapest way. Okay, let's see. Let's start at the beginning. We need to read this data. And what worked well the last time is to have a read from file and something like read from string. This one gets some input string. This gets a file name. And then we open this file, read all text, trim it, and pass it into read from string. Now we need to remember what we want to, or we need to come up with what kind of data do we want. And I mentioned lists of. And now it's more interesting. What do we need to save? I think we need a data class right now. And what's it? It's called a position. What do we need? We do not need the X and a Y because this is encoded in the list, but we need the risk level. This is all we need for reading. And then at some point we might also want to remember more things. And the thing we might want to remember is where did we come from? Let's say if we are here at 2. We need to remember that we came from here. If we visit this thing. And if we roughly follow Dijkstra, the way I remember it, if it's correct, is we need to remember what was where did we come from, like from here, and what kind of cost was that? What was the risk, the total risk up to this point, so that we end up with, if we end up by another way that we can compare, is this one cheaper? So we came from a pair, I guess. This is the X and Y. Maybe create a data class for this as well. It's a point. with an X and a Y. And then we also need a cost. Or total risk. Total risk. This is the risk if we came from this point. What was the total risk to end up here? And I guess the point is actually nullable because initially we do not have any. And the total risk, we are looking for the lowest one, so we should probably pick a high one to start with. Why companion? Why is there no Mac? Oh, this is just a type. I'm sorry. Max value. Yeah. So we had a list of lists of position. And that is essentially what this read from string will return. So we use it for in read from file. And this is a to-do. And let's write a test. Let's write our first test just for reading the data. This is our input. Oh, how do we call it? Is it just a list of lists of positions, or do we need more? Do we want to wrap this into something better? I mean, instead of adding all of that stuff to the position, we could also have maps, multiple maps, I guess. Actually, I'm wondering if we might want to add the point as well, because it will help us to navigate. This is just for the quick access. But then this could also be inside a map. Well, we can still change this. Doesn't seem important right now. So our, what is this? A cavern is read from string input. Now we can run this once, and this will now fail because we haven't implemented anything. So to implement this, it's again going by character and by lines. Quite straightforward, I guess. Input lines for each map to a list of points now. So we have a line, and for every line we say give us the list of characters, and the list of characters we map to its digit, and that will be a position of containing How can we write this better? Maybe we need to wrap this after all. Map indexed. We need the index as well. The index will be the y, and the x will be here. Map indexed. This will be the x. Then we return a position with a point xy, where I'm still not sure if we need it, and we will need the risk level, which is the character as a digit. And then we return this. Okay. Let's test this. We run this. It's green, but we didn't assert anything yet. So let's assert something. The top left will be cavern 0, 0. And we assume it has a 0 at top left point x and at y, and we expect the risk level to be 1. And we expect a max total risk and we assume that we have no path to it. That is working. Let's pick another one. How large is this cave? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. So if we say, is the 10 here as well? Yeah. So 9, 9 should be 1 with 9, 9. And that would be the bottom right. Oops. We need to put in bottom right here. Okay. Let's try one more. If we say 0, 9, and this will be 0, 9, and that should be the bottom left. The risk level is 2. And then let's also do the top right, and then I'm okay with it, and I won't test any other things. Bottom right is 9, 0. Top right, sorry. And this should be 9, 0 here, and we expect the risk level to be a 2 as well. Run this. We made a mistake somewhere. Expected a 0 here, but it is actually at 9. Bottom left 0, 9. This is not the bottom left. The bottom left. It is the bottom. No, it's not. Why? Okay. Confusion. We say the first number is, what is the first number here? Every line is the y. And for every y, we have a bunch of x's. This is correct so far. So if we want to navigate, we need to navigate by, not by x, y, but by on the y array first. So if we want the bottom left, we need to say this is 9, 0. Oh, that will probably be a problem at some point. And the top right will be 0, 9. That might cause some issues, because they kind of feel reverse. It's yx, and here we have xy. If we ever throw in a point into this array, we need to be really cautious what we do. Okay, but we can read a string. Nice. And we have some very basic data structure. Do we want to write the code to print? Maybe it's less interesting right now because there is no path yet that we can print. But we could already start with that. Dump. For that we want to return a string, and we only need to reverse this. So we need a build string, and then we kind of just loop. So for each, in this case we have this again a line, I guess, and then line for each. We have a position, and then we append the position, and after every line we append a line ending. Oh, and we need for each is now a for each inside the build string function. So that's not nice, but let's create a variable for that, and then we test this. Why is the formatting not working as it should? What the hell? Huh? Did I do anything that caused this to be test dump? But can I have a tab size of 4 again? What the hell? What did I break? Okay, there is definitely an error over here. That is just a return. This is enough to get a tab size of 4, please. I will create a new test class. Go to test, create a new test, and that is day 15 test. Now I'm curious what's going to happen. All right, I'm officially very confused. If I copy this over, I don't know what happened, but this one is now, the tab size is forever 8. we just continue using this one now. I have no time for this. Okay. Let's test the dump function. We read this cavern. Let's make this a little bit shorter. And then I guess we want exactly this out again if we dump it. I mean, we do not need to print it right now. We might not even need to print it at all. But this will be helpful when we debug. And to be honest, if we get to the right solution, I would like to see the path. Okay, what is wrong? Yeah. Okay, we are printing positions. That is not what dump is supposed to do. It is supposed to just print the risk level. Not a problem. We have a new line. Oh yeah. That has happened so often. And the easy way out is we just trim our string we just created. Awesome, that works. So now to the fun part. We need to find the path with the lowest total risk. Find path with lowest risk. We want this was, well, we're thinking, should I make it an extension function? But I feel like this might make it weird to read. You know what? I'm thinking we might want to actually create a cavern class. Because accessing those things, that will be very annoying in this list. We might want to have some helpers on a class that help us with that. So this is a cavern. Oh, now we can move dump into the cavern class, which is nice, I guess. Now we do not need this anymore. This is now supposed to return a cavern. And we can wrap that. And this returns a cavern. Now we actually do not need to wrap this. Return. We wrap this whole thing. We still write this as an extension function, I guess. Doesn't need to. Can also be in the cavern now. Find path with lowest risk. Okay. Now our test is probably broken. But the nice thing is now we can now have a getter with x and y which returns a position. And now we can just reverse it here. We will not need to care about, will not have to care about how this is to be navigated. Now we can even implement this for position. And now it doesn't matter that this map is this way and blah, blah, blah. Because, yeah. Otherwise, if we need to flip this all the time, everywhere in the code, that will be so shitty. So now we just say, hey, get position 0, 0. Or get 9, 9. Or get, and now it's fancy, 0, 9. Get 9, 0. Now we can reverse it, and the IDE will say us this is X and this is Y. So this hopefully still passes. Yes, it does. Okay. How do we want now to find the path with the lowest risk? Let's copy some of this. Let's create a simple example. And then we make this just 4 by 4. And we can only go, yeah, we cannot move diagonally. That is good. So we need a start position and an end position. And we also need to somehow remember things. Let's say we start here. And then let's start, the only way we can go is here and here. Doesn't matter which direction we are going in. But we need to remember if we are here, where did we go from? And how expensive was it? So if we are here, we find all the neighbors we can go to. We calculate the risk. And then we continue with the path that has the lowest risk at the neighbors, and then again find the one in our queue with the lowest risk, and we always pick the lowest risk path until we might be at the end at some point. So if you have a position, we also need to know, is it the end? One is start for a position and is end for a position. This one is easy. If it's if it's 0.00, that is nice. For this one we need the size. Oops. I've implemented this a couple of times already, so actually There's no need to calculate the size all the time. So let's make the let's create a val for that, and it's a lazy one. And it's a point. Could be a point. Will it be a point? Will it be a pair? Maybe it will be a point. We're kind of misusing point here because it is not a point. We do not want to create a new type. Should it be a pair? And we do not have x and y, so we make it a point. The x and the y. So if we take the map and the size, this is the y. And the x is if we take the map and just the first row and the size of the first row. Since all rows are the same, this is enough. And so for the end, we only need to say if this x is the size x, and if this position y is the size y, then hey, this is the end. Yay, awesome. This is a boolean. Quick tests. I mean, the start one will be a bit simple. A third true for cavern is start position. Oh, do we actually want a position or a point? Maybe a point, because everything else is maybe annoying. And this is point with 0, 0 should be true, and let's create some false ones. Let's create the combos, I guess. And let's do the same for the end. Is end. And now this is false and this one is true. And then let's run all tests. And this one didn't run. Okay, let's run it. Oh, test end is broken. Why is this the case? Because the size is 10, but the position is 99. All right. See, it was helpful to create the size. All right. Back to actually implementing the path algorithm. We said we need to start at 0. Oh, another interesting point. If we read the risk level of the first one, then it's already max. And I guess if we start at max, then we might not want to go there again. I mean, we might have, at the start position, we might have a risk level of 0, right? Yeah, we need to. And I think it even said somewhere the start position is not even counted. So I guess we need to. What is wrong here? This one too much. When we need to change position 1 immediately. How do we even want to allow updating? So I guess this one needs to be a var. This one needs to be a var. And then we say we need to update the risk level. We could just do get 0, 0 and say total risk here is 0. Did this affect any of our tests? Yes, it did. And that makes sense. We want to say there's no total risk here yet. All right, back to actually implementing the path. So we need a list of the positions we want to go by. Let's say to visit, maybe. Those are the things we still need to visit. And we start with the starting position and then we add those two. And this list always needs to be ordered by its risk level so that we always expand the path with currently the lowest risk. So maybe it's something like a visit queue. It's a mutable list. And we could use one of those Java types, I think, that are always sorting the lists, which might be helpful here. Or we always sort the list afterwards, which might end up being a long one, maybe still fast enough. Let's try just using the simple approach of using a list. So we have a list of, is it just points or positions? I guess we keep the whole position in it because then we have the risk level. And then we say while visit queue is not empty. And while it's not empty, we need to do stuff. And we also need to add our start position, which is 0, 0. Now, how do we remember if we visited something already? Because let's say we it doesn't matter, I guess, because if we visit something again, let's say we go this way, and it's not a smaller path, the total risk is not smaller, and we do not need to visit it again anyways. So we kind of use the total risk as a mechanism to determine if we need to visit this thing again. But if let's say we went down this route and we somehow end up going this route and it's now cheaper to go here, and we do not need to, we might need to, yeah, maybe we want to go to this point. Do we need to go to this point again? This is my question. Let's imagine a world where we ended up here and then we find a better way to end up here. Then we might need to start from here again, right? Because it might be cheaper now. The follow-up might be cheaper now. But can this even happen that if we end up here with the cheapest path, then there's no other path that gets here cheaper. Is this correct? Not necessarily. If we have a path that is this, and then, oh, this is more expensive, we do not go this way. But then this is a 9. Well, then we still can't go here cheaper, can we? Or can we not? Do we need to visit a path again? No. We do never need to visit a node again, is my theory, because if we ended up there, it is already the cheapest path we are currently following, so there cannot be a cheaper one. So we need to somehow remember the things we already visited. We can put them into a queue, a list, a map, or we could just remember it here. Just super cheap to keep, so let's just do it this way. So this means we need a place to visit, and this is the first element. Can we? Yeah, we can remove it and get it. That is awesome. And we say, hey, this position, by the way, it's visited. Never visit it again. Then we get all the neighbors. Get neighbors. And then for every neighbor, what is the total risk? Every neighbor, if not visited, let's say this. We have not visited this neighbor before. Then we say, hey, the total risk to visit you is my risk plus the risk up to this, like the total risk the total risk here is 0. The total risk here is 1 because we moved 1, right? The number is the total risk of the add up the risk to each person you enter. Okay, if we enter here, then your total risk is my total risk plus your risk. Or let's say neighbor risk. Maybe just call this current. And then we said it is the current total risk plus your risk. And then we add neighbor to Q, and then we sort the queue, and then we start with the next one, that is the lowest risk. And we also need some kind of exit. If current is the end, return. Ta-da! The thing is, then everyone knows where it's coming from. Then we also need to backtrack to actually find the path, because we have the end, and from the end we know the previous one, and we need to do this until we are at the start. That's a different kind of problem to solve. Actually, the interesting thing is, for this one, we only need the total risk, so we do not even need the path anymore. That is interesting, yeah. How about this? We say we return a path, and this one has a total risk. And for now, it's the only thing it has. And if in part 2 we need more than that, we will return it. We will add it to this path class. Okay, let's try that. If this is the end, return path of current, and this is the total risk. Ta-da! You did it! Congratulations, everyone! If we end up here with nothing, that is weird. Empty queue, and we didn't find the end. We should never end up there. Okay, we did this. Now the famous neighbor function again. I wonder if we should just steal it. Neighbor. It is a list of positions. And it's the top, left, right, and bottom. So list of get let's maybe create some helpers, otherwise this is going to be annoying to write. We need an X and a Y. This is the current position. We want to get the neighbors of. And then we need position X, Y. Let's start with the top, then the left, then the right, and then the bottom. And then we only want those that are valid. And valid points are where position point X is larger than 0 and position point X is smaller than size X, and where position point y larger or equals 0 and position point y is smaller than size y. And this is overloading position, so we use current. And now I guess we need to write a test once again. And we should have written some kind of navigation library that we can reuse. And since this is my first time participating in Advent of Code, I'm not actually sure if this is maybe intentional. And to solve the later days, maybe it is actually helpful to have generic libraries of the things you did before. Okay, let's see. We have this cavern. Let's give us the neighbors of 0, 0. Top left neighbors. Left neighbors size 3. And we need to reverse that. 3 top left neighbors size. Next out of bounds. Okay, we did something wrong. Oh, the getter. We might need a get or null here. Because then we can say get or null y and get or null x. And now we do not even need to get or null. Let's take a quick peek. Get or null returns an element at a given index or null if the index is out of bounds. That is exactly what we want, and then we can map not null or filter not null. List of not null, even better. And then we can simplify this and run it again. Go. It's 2. Oh yeah. Good point. We can only go top, left, right. So this should be 1 and 1. Let's pick a random point, 3, 3. So this one should have 4 neighbors. If we pick 9, 9, then this one has only 2 again. Run this. Lots of errors because we didn't change the name. This is random neighbors. This is bottom right neighbors. Run. Okay, back to our algorithm. Okay, now we need the neighbors. Neighbor of current and then neighbors can actually keep that, and then we say filter where position is not visited yet. And then we loop over them. And say your total risk is now the current total risk plus your risk level. Is this correct to do this now, or should we do this when we visit it? No, that is fine. And then we say visit queue at this position. And once we are done, we say visit queue sorted by total risk. Now we should pick up the one that is the lowest, continue until we find an end. Let's see. Suddenly it was so quick to write this code. I'm curious if it's actually working. We have only one example though. So even if we find this path, it's not many test cases to have confidence that it's working. And we get a path if we say cavern find path with lowest risk. Path total risk. It's printed and we already know it should be, I think, 40. Is this correct? Yes, it is. Did we get 40? Maybe we got an endless loop. How can this be? We should run out of positions. So let's start by just printing what we visit. Visiting current point queue visit queue size. Let's see, what points are we visiting? Oh wow, the queue is so large. And it's not getting smaller. Remove first. Is it not doing what it's supposed to do? Removes the first element from this mutable list and returns that removed element or throws. Do we visit some positions again? Let's also look at the risk. Well, the size is, we take the 10 by 10, so the queue can never be larger than 100. So what the hell is in this queue? Can we search in here? Yeah, let's say x equals and y equals 1. So we visit the same points multiple times. That is not good. Yeah, one reason for that is we are adding points to the queue that are already in the queue. That's not something we should do. How can we do this? Adding. Still surprised we are adding this point again. Okay, that's enough. Let's say x equals 6 and y equals 1. This was the point. Here we are adding it, 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 and we are adding it, and we are adding it, and we are not even getting there. Here we are visiting it, then we are visiting it again because it is already in the queue, and then we do it again and again at all the other points again, so it gets huge. Yeah, we need to prevent adding it again. We could be lazy and create some cute. We could make the queue smarter, or we could actually do if it's already queued, we do not need to queue it again. We need to update the queue, the total risk, because we need to sort again. If it's not queued, then we queue it, and we never need to queue it again, I guess. We only update its risk so that it might move higher or lower. We found a path. It's unfortunately larger than expected. Well, I'm at least happy we found a path. Kind of almost quickly. But it's not 40. Now the question is, do we want to visualize the path and get the path? Stop. I know why it's wrong, I think. If it's the end, we still need to update it. But that doesn't help it. No, we already updated it because we went here. $57, this is 17 too much. So we found a path, but apparently not the best. How can this be? If the point is queued, and we get to this point again later, well, once we visited it, there's no reason to go there again. So that is not the problem. Is there a reason why we could add 17? Not really. Even if we added this and forgot the end, that is not a difference of 17. So we need the path after all. So we need a helper for that. Struct path. We want a path in the end here. And which is position in this case. And then path will get a list of positions. And this will be an ordered list from start to end. And then we need what do we need? We need this list. Mutable list, positions, and then current is the end position, while not is start current, positions at current, and then current is now positions. Oh, I think I have an idea. We only update the total risk if it's lower. It's a position we already have seen. Risk or total risk. It is this. And if total risk is smaller than the total risk of this position, only then we update total risk. And what I forgot to do is to say this. Then we came from this point. Before we construct the path, let's run this once, because maybe we are at 40 now. Current is current from, because that is what we were missing here. Throw illegal. State exception. No path from current. The problem, current is a position, current from is a point. Let get point. Get it. We need a point. Need a way to get from a point to a position. Okay. Now we did run it after all, and then the path is the path of the total risk of the end and this list of positions that we just created. Awesome. Let's run this. And now we need to say construct path from this. Okay, we found a path and it is now 40. Okay, we might be able to do it. Let's get rid of the prints. We found the total risk. Woohoo, this is awesome. Do we want to print the path? It's essentially not readable. Let's run it on part 1. So we have a cavern, which is read from file of day 15.txt, and then we say cavern, find path with lowest risk, found path with risk level So now I'm excited if this will work. That's it, it's already done. 388. No, it's not the right answer. The answer is too high. Curiously, it's the right answer for someone else. You might be logged into the wrong account or just unlucky. What? In any case, you need to be using your puzzle input. If you're stuck, make sure you're using the full input data. Your answer is too high. Curiously, it's the right answer for someone else? Is this just a joke or what is going on? Too high. Okay, this is kind of annoying because we solved the test case correctly. We solve the actual day problem, but it's not the best path, apparently. I guess we need to start to print the path. It said it's too high, so we need a lower path than the one we found. Is there a quick error we can see here? We go to every neighbor. If the new total risk is lower, let me take this one. Say this is the best position to get there. If it's not queued, we will queue it. And we will sort it by the total risk. And pick it. Yeah, no, I'm not sure. We might need to print it. Let's start by maybe dumping the whole thing again to see if just our input and output is correct. So if we read, or let's actually read it from the file. Our cavern is read from file day 15 txt. And then this should be the same as Now let's load the file. Tear it here. And let's see if this is dump file, if this is the right file. Okay, that works. Now we can print the path, and maybe we'll just replace it with another character. Let's say, what if it's like this? Is this easy to read? Potentially it is. Maybe, are there other characters? 0 would be not easy to read. Else can we use an add? Yeah. Maybe something small actually. Dot. Yeah, dot might be nice to read. Let's try this. We print a dot for every visited node. There's actually one thing I would love to try first. What if we reverse start and end and search a path from the end to the start? Do we get the same path? How can we do this easily? Let's try the following thing. We need to start. Do we need a start point or a position when we find the path? A point for the end, and for the start we can also work with a point. So start is a point at 0, 0, and end is point size -1, or size x -1 and size y -1. And here we can now define a start point and an end point. And we throw in this start. And the end, by default this is start, and by default this is end. Start point and end point. And we use start point here. And instead of isEnd, we compare if the current point equals end point. So let's make sure we still get the same result. If we execute this, this will return 40 still, right? Yes, it does. And this one probably still returned 388. Yeah. And if we now passing those points, this will still be the same. We look for something that from start to end. Yes, and now we reverse them. Does this still... Wow, this finds a negative start risk level. So that kind of indicates that something is kind of going wrong, because it should be fairly similar, because we The only difference is that we do not take the 2 here and we do not take the 4 here. But apart from that, it should still be the same value that gets out of it. The cheapest path from here to here, if it's the cheapest, then the backwards way should be the same. Right? Is there any reason? If there's a cheaper way from the bottom right to the top left, then the top left could take the same path to the bottom right. So this should be the same. So, okay, we are one step closer to finding the issue. Now the question is, why is our neighbor function maybe doing the wrong thing and we're looking at the wrong neighbors? If we have an x and y position, which is this, then we need to look one below, or -1 is here, then x -1 should be here on the left, x +1 should be here, and this one should be y +1 on the bottom. I think that looks good. And we had a test for that as well, right? Yeah, we didn't actually look at a specific point. Maybe we should do this too. It feels correct. Top. This is left. This is right. This is bottom. And we get or null, which means we get from the y, and then we get the x. Seems right, yeah. Yeah. Let's take another look. Maybe the reverse is not... yeah, let's do something else. Test find path with lowest risk. Reversed. I'm curious if in the small example that is correct. This is maybe doing something wrong too. Then maybe just our reverse is not working correctly. Okay, reverse is returning something negative as well. So we can work with the simple approach. So we at the start point. If this is not empty, if this is the endpoint, we construct a path from the end. We need this here too. This is our problem. While the current point is not the start, point, continue. Oh, and then we need to path in from end back to the start point. Well, in this case, I guess we can use the point then, so that we do not need to look up the position for no reason. It's still negative, and this should only construct a path. It's not about calculating. Oh, I know what one of the problems, I think. We never changed the total risk of the start position. Somewhere here we had code that... Was it the code that reads it? This sets the total risk to 0. We don't want to do this here. Instead, we want to do this. I guess when we find the path, we could do it. So start equals get the start point. And we can say the total risk of this start is 0. That's where we start. And I'm still curious why it becomes 0. This should still happen, right? No. Now it's right. Okay. It's still 40. That's good to know. Now I'm curious if it's for part 2, if it's still part 1, if it's still 388. If you go the other way. It's 386, but we start from 4 instead of 2, so it should be 2 less, which is exactly the thing. So if we find exactly the same path, so I'm super surprised why 388 is not the right answer. Let's print the path. Guess we allow doing something like throwing in a path. Does this contain a bunch of positions? Okay. If position point in, or if position in path positions, then we append a dot. Else we append the risk level. And the path is nullable. Might not always have a path. If path is not null and the position is in the positions of the path. Okay, now we can print our path. Take a look at that. Cavern dump path. Then let's run this. All right, let's take a look at the path we found. Looks quite nice. Do not really see what kind of numbers we omit. Yeah, that is maybe a problem, because it would be nice to know, like here, would it have been cheaper to go this way, or are those ones as well? Guess we could make it larger. How can we do this? Just as a test, I guess we could do if it's if it's the path we are going, we put this into square brackets. Otherwise, it is empty. So now we circle, kind of circle the right arrow, but this will make this thing super huge. But that is not the problem if you just want to read it once. So we go this way, we follow the ones. There's a 6 here, which is expensive, but there's no way around it that I can see. So 1 here. This is a 7. And instead of going the 7, we could go 1, 3, 6. This is only 6, right? We should also circle things we visited, maybe. If position visited, else this, oof. IntelliJ tries to be smart and add some brackets, which is confusing. Okay. If it's visited, we still mark it with maybe those brackets. Oh wow, did we end up visiting everything? That is weird as well, like, why would we ever go to this corner? Is our... Now I have an idea. Sorted by... It doesn't sort in place, right? It returns a new one. Turns a list. Damn it. Yeah, we sort the queue and then we do not use it at the end. So we were super lucky that it actually worked in the first version. So here we might need to say, hey, this new one. And it needs to be mutable again. Now let's look at the thing again. Our path is smaller, that is interesting. Yeah, there are some we did not visit here. Where was the thing we didn't look at? Was it the 7 here? Yeah, I think now we are walking around the 7. It's interesting, in the beginning we didn't visit stuff, but then we pretty much visited all of them. Then we go here. This 9 is kind of scary, but every other way there's a 9 in the way. There we go. It's interesting that we ended up with a pretty nice path regardless. And now we didn't... Oh, this is still the reverse and it's still 388. Let's go back to from start to end. $386. Why is the first one not in our path? Let's fix that too. Path. And then at the end we need to add the start. Get start point. Let's get the whole path. Yeah. We are walking around the 7 still. The path looks pretty nice. And we still ended up visiting everything, which, yeah, kind of makes a little bit sense, because as soon as we go down here, where we have, I don't know, let's say here the total risk is 10 or whatever, then suddenly the 8 becomes cheaper and we can go the 8. As far as I understand it, that is just how Dijkstra works. And if we would use A star, we would more try to continue into this direction instead of just expanding into all directions, depending only on the risk level here. But the most interesting thing is we have a number that is smaller, and it said your number is too high. Now we have 386. What does adventofcode say to that? That's the right answer. Awesome. Correct. Yay. Let's fix that. This was for debugging purposes. Let's say there's a boolean. Default it's false. We say if debug, and we do this stuff again. Otherwise we just print position risk level. Let's look at this again. Okay. Let's continue from here. Part 2. Now that you know how to find low-risk path in the cave, you can try to find your way out. The entire cave is actually 5 times larger in both directions than you thought. The area you originally scanned is just one tile in the 5 by 5 tile area that forms the full map. Your original map tile repeats to the right and downward, and each time the tile repeats to the right or downward, all of its risk levels are 1 higher than the tile immediately up or left of it. Okay. However, risk levels above 9 wrap back around to 1. Oh my god, so if your original map had some positions with a risk level of 8, then that same position on each of the 25 total tiles would be as follows. If your original had some position with a risk level... each single digit above corresponds to the example position with a value of 8 on the top left tile Because the full map is actually 5 times larger in both directions, that position appears a total of 25 times, once in each duplicated tile, with the value shown above. Here's the full 5 times as large version of the first example above. The original map in the top left corner highlighted. Equipped with the full map, you can now find a path from the top left corner to the bottom right with the lowest total risk. Awesome. So we need a function that expands our path. Huh. Yeah, let's write that. Do we do this? Maybe add this to the cavern again as a function. Say expand. Do we need to care that it's 5? Maybe not. Question is, how do we want to expand it? Yeah, let's add it times. Okay, so we need a new cavern. Let's do that. Where's the function here? Turn a cavern. The cavern contains a map of lists of positions, and that's what we need to rewrite. Positions is mutable list of a mutable list of positions. This is a mutable list. And then we loop. We say times, no, repeat times. Then we say we need to loop over our original map. And then for every time we index so if we do this 5 times now, we have essentially a copy. We need to copy into both directions. What we could do instead is we could move over the list and then copy those over into all the positions. And then at some point we return a cavern with new positions. Y in positions is this the way we want to loop? Or let's say size Y. Zero to size Y. Oh, this is until, I guess. Oh. So it's smaller than size, and then for x in 0 until size x. Then we have a position. Current, that is from our map. Say new map, just to make it more obvious. If you access positions, it can also be the position of the thing we are in. So let's say instead a map, and then we want y. Actually, could say get xy. Now we need to copy it in 5 times in this direction and 5 times to the other direction. For shift y in 0 until times, and for shift x in 0 until times. Now we just copy this over, which means new map x, no, new map y x equals, stop, new map y plus shift y plus x shift x. And now, how was the algorithm? Each time the tile repeats to the right or downward, all of its risk levels are 1 higher. So this is a 1, this is a 3, which means it moved 1 here and then 1 here. So this is a 3 now. So essentially we need to say it is a copy of current, or let's just create a new position. It's a position new y is y plus shift y. Our new x is x plus shift x. So we move this over. And it's, we need the point. And the risk level is current risk level plus shift x plus shift y. Now we need to wrap it as well. Risk levels above 9 wrap back to 1. Okay. It's actually a wrap kind of function. No, that would be shift. This would be mod 9. What's the problem with shift y? Value is always 0. Why is it always 0? It's inside this. Come on. It's 0 until times. In the first loop it's 0, yeah, but not in the next one. What are you talking about? Is there anything else we need to change? Queued, visited, no. Okay. Wait, shift 9, is this correct? Mod 9, is this correct? Let's create a scratch file. I'm confused right now. If my value is 5, then 5 value mod 9 is 5, and if value is 9, it is 0, so that is wrong. 10. Oh, sorry. It need to be 10 then. 9 is 9, 10 is 0. However, risk levels above 9 wrap back around to 1. Wait a second. Okay. So they wrap around. The problem is mod does not work that way. If it's 9, then it starts at 1 again. So mod 10 would be wrong. It starts at 0. Isn't there a function that does, was it clamp? Curse in. Curse in sounds interesting. Ensures that this value lies in this range. This value, it's in the range, or if it's less than minimum value or maximum, if it's value greater than maximum value. No, that will throw. Could write a helper, I guess. Int, I think clamp is the word for it. Max returns an int while this is larger than max. Current is this, and current, while current is larger than, then we remove max. Let's write a test for that. I kind of almost expect it to be a Kotlin function, but it's also quick to write. One of let's test the whole thing. It's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and let's do 12 as well. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, this should be 1 now. Should be 2. This should be 3. Is this what this does? Oh. Clamp 9. Test. Make this smaller again. Whoops. Created a nice endless loop. Yeah. Current equals current minus max. We can use minus equals and let's go. It's not a var. That doesn't work. Let's do this again. Okay, the thing does what it's supposed to do. Yeah, let's run this and see if it does what we think it does. But this here is still confusing. Value is always 0. Why does it think that? Should not be. Let's see. Test expanding small cavern. Let's take the small one. Let's read it. New cavern is cavern expand 5. Then we print it. And it didn't print anything at all. Oh, because we are running print clamp, test clamp with this one. Index out of bounds. Yeah, that makes sense, I guess, because we didn't create a list that is large enough yet. So for every y, we first need to say new map y equals mutable list of. Get a mutable list at all the positions. This is now a bit awkward. Can we create those with the size? Maybe want an array instead. Can we create an array of that size and then turn it into a list? Array of int array. Sizes size y times And then what is the init function doing? Oops. The function init is called for each array element sequentially starting from the first one. It should return the value for an array element given its index. That is constructing it differently. What's the nicest way now to build this? The problem is we are creating this list with positions, and then at the end there we try to copy this first element to all the positions, to all the first positions, but the lists are not that large yet. We could try to initialize those lists accordingly, and those classes are annoying. We could initialize the list accordingly first, but we do not have values, so we would need to initialize it with nulls, and that is awkward. Instead, we could try to build a new map immediately. And while we fill the map, we get the values from the original map. Maybe the other way around, it's actually easier. So instead, we do this. And then we say, go away. Then we do it almost as if we are reading our file. Where did we write this? Yeah, and essentially we are writing that. Let's see. Where's our expand function again? Here. So we reverse this. We have a mutable list of a mutable list of positions. And whenever we go through this, we have a mutable list of positions. And then we say add this line. And then at the end we say return a cavern with those lines. And the other code is not needed anymore. So let's take this, and then we need the source point. The source point is getting the current, we need to translate the x back. Translate x, translate y. The x is x divided by size x. And then the y is y translate mod size y. And then we get the x and the y. It's of the translation though. Let's test this. Our Scratch file. Let's say our map is 5 by 5, which means we have index 0 to 4. And we have 0 mod 5, and then at some point 4, and then 5. Let us run, and then at some point, if he does 5 times, we might have 25. Awesome. And now we also need to know our shift, how often we have shifted it, which is so it's kind of divided by 5. 0 divided by 5. 5 divided by 5. 25 by 5. So we need to divide it by the size. What the hell? What is this crap? And if you have something like 4 divided by 5, they will all be 0, which is exactly what we want. So the shift is size of, no. The shift is our x divided by times and y divided by times, right? Let's say if this is 10 times. No, it's the size. That was bullshit. Where's our file? Divided by the size of the smaller one. So we need to add a position, which is at point xy, and has a risk level of, we wrote here already, the source risk level plus the shift and this clamped. line. Get rid of this. And why does it not use times here? Because we hard coded it to 5. Okay. Time for a test. We expand a small cavern. It looks like this. Now we need to figure out if this is actually what we needed. New cavern dump should look like this here. Let's run this. And let's fix it and run it. Okay, we can expand it. Now the big question is our algorithm still good enough for the expanded version? And I think it does, because we did not go with the brute force, like going all the directions possible. We visit every point only once, and that still looks good. Oh, let's test actually on the small one. Find steal this somewhere. This one. Now this is test find path with lowest risk expanded. This can still be start and end. Expanded cavern equals cavern expand 5. Now we search the path in here. And we expect this to be 315. We did not run it. Let's run this one. 315, that looks good. And was nice and fast. Let's do this here as well. We find the path with the lowest risk, and then print that. Expand by 5. No, that is wrong. What did I do? We want to use the expanded cavern here, like this. Do not want to print it. And we get 315. That would be smaller than before. Is this really the case? It is not the right answer, it's too low. Yeah, was expecting that. Why is it too low? Time to print it, I guess. Oh, interesting. This way. Oh, we're executing part. Wait a second. We were executing part 1 and it gave us 315. Forget it. We were running. Whatever. Let's go back. Oh my god. 386, still correct. Now let's actually execute part 2. It's taking a while, but we actually printed it by accident. But since we did this now, let's actually try to take a look. Did we only print a small part of it? I will just ignore this and print, try the answer. Yeah, that's the right answer. Awesome, we did it. We had one small bug in our pathfinding that caused this little issue here. I already forgot what it was. What was actually the problem? Oh yeah, we did sort the queue and then still use the old queue. That was stupid. Was good enough for the example, but not for the big one. All right, yeah. Let me know how you solved the problem, if you were able to solve it, if you maybe implemented A star. I'm curious if you implemented A star, how much better it looks if you print your cavern, because if I go back to printing the debug version of part 1, and you could see that we found the path here nicely, but we expanded into ridiculous directions, like going all the way to the right, which might not be what A star does. Or we might try to first find nodes along the path or in the right direction before we go into weird directions. I guess that would be not hard to add to the current code, because we have this queue that goes by total risk and always picks the one with the total risk. For the queue, we could add the distance to it. So calculate how far is the point from our end, and if we pick a point, or if we sort the list, we use the combined total risk and the distance, and then we would kind of also prefer points that have a low risk and are closer to have a smaller distance, essentially. Anyhow, I will remove some of the comments and the debug statements in between, and then, as always, upload this to GitHub for you to check out. You can find the link in the description. If you like this video, please leave a thumbs up. That will help me, and yeah, see you tomorrow. Bye bye.